Parametric methods model selection procedure. There are a number of procedures we can use to fine-tune model complexity. In practice, the method we use to find the optimal complexity is cross-validation. We cannot calculate the bias and variances for a model, but we can calculate the total error. Given a dataset, we divide it into two parts as training and validation sets. Train candidate models of different complexities and test their error on the validation set left over during training. As the model complexity increases, training error keeps decreasing. The error on the validation set decreases up to a certain level of complexity, then stops decreasing or does not decrease further significantly, or even increases if there is a significant noise. This elbow corresponds to the optimal complexity level, see figure 4.7. In real life, we cannot calculate bias and hence error as we do in figure 4.6. The validation error in figure 4.7 is an estimate of that, except that it also contains noise. Even if we have the right model that there is no bias and large enough data that variance is negligible, there may still be non-zero validation error. Note that the validation error of figure 4.7 is not as V-shaped as the error of figure 4.6 because the former uses more training data, and we know that we can constrain variance with more data. Indeed, we see in figure 4.5d that even the fifth-order polynomial behaves like a third order where there is data. For example, at the two extremes where there are fewer data points, it is not as accurate. Another approach that is used frequently is a regularization. In this approach, we write an augmented error function, E prime, which is equals to error on data plus lambda times model complexity. This has a second term that penalizes complex models with large variance where lambda gives the weight of this penalty. When we minimize the augmented error function instead of the error on data only, we penalize complex models and thus decrease variance. If lambda is taken too large, only very simple models are allowed and we risk introducing bias. Lambda is optimized using cross-validation. Another way we can view equation 4.37 is by regarding E prime as the error on new test data. The first term on the right is the training error and the second is an optimization term estimating the discrepancy between training and test error. Methods such as Akaike's information criterion (AIC) and Bayesian information criterion (BIC) work by estimating this optimism and adding it to the training error to estimate test error without any need for validation. The magnitude of this optimism term increases linearly with d, the number of inputs. Here it is k plus 1, and decreases as n, training set size, increases. As training set size increases, and it also increases with rho square, the variance of the noise added, which we can estimate from the error of a low bias model. For models that are not linear, d should be replaced with the effective number of parameters. Structural risk minimization, SRM. This is proposed by Vapnik, 1995, uses a set of models ordered in terms of their complexities. An example is polynomials of increasing order. The complexity is generally given by the number of free parameters. VC dimension is another measure of model complexity. In equation 4.37, we can have a set of decreasing lambda I to get a set of models ordered in increasing complexity. Model selection by SRM then corresponds to finding the model simplest in terms of order and best in terms of empirical error on the data. Minimum description length MDL uses an information theoretical measure. Kolmogorov complexity of a dataset is defined as the shortest description of the data. If the data is simple, it has a short complexity. For example, if it is a sequence of zeros, we can just write 0 and the length of the sequence. If the data is completely random, then we cannot have any description of the data shorter than the data itself. If a model is appropriate for the data, then it has a good fit to the data, and instead of the data, we can store the model description. Out of all the models that described the data, we want to have the simplest model so that it lends itself to the shortest description. So we again have a trade-off between how simple the model is and how well it explains the data. Bayesian model selection is used when we have some prior knowledge about the appropriate class of approximating functions. This prior knowledge is defined as a prior distribution over models, P of model. Given the data and assuming a model, we can calculate P of model conditioning on data using Bayes' rule. That is, P of model conditioning on data equals to P of data conditioning on model times P of model divided by P of data. P of model conditioning on data is the posterior probability of the model given our prior subjective knowledge about models, namely P of model, and the objective support provided by the data, namely P of data conditioning on model. We can then choose the model with the highest posterior probability or take an average over all models weighted by their posterior probabilities. If we take the log of equation 4.38, we get log of P of model conditioning on data is equals to log of P of data conditioning on model plus log of P of model, then minus some constant C, which has the form of equation 4.37. The log likelihood of the data is the training error, and the log of the prior is the penalty term. For example, if we have a regression model and use the prior P of W, which is approximated by the normal distributions of 0 and 1 over lambda, the MAP corresponds to the MIMA of 4.40. That expectation is equals to the summations of R to the T minus G of X to the T conditioning on W, then to the square, then to the summation summing for index T, plus another term which is lambda times the summations of Wi to the square summing for index I. That is, we look for Wi that both decrease error and are also as close as possible to 0, and the reason we want them close to 0 is then because the fitted polynomial will be smoother. As the polynomial order increases, to get a better fit to the data, the function will go up and down, which will mean coefficients moving away from 0. See figure 4.8. When we add this penalty, we force a flatter, smoother fit. How much we penalize depends on lambda, which is the inverse of the variance of the prior. That is how much we expect the weights a priori to be away from 0. That is, having such a prior is equivalent to forcing parameters to be close to 0. We're going to talk about this in more detail in chapter 14. That is when the prior is chosen such that we give higher probabilities to simpler models following Occam's razor. The Bayesian approach, regularization, SRM, and MDL are equivalent. Cross-validation is different from all other methods for model selection in that it makes no prior assumption about the model if there is a large enough validation dataset. It is the best approach. The other models become useful when the data sample is small. Notes: a good source on the basics of maximum likelihood and Bayesian estimation is Rose 1987. Many pattern recognition textbooks discuss classification with parametric models. Tests for checking univariate normality can be found in Ranger 1995. Also, there is a book discuss bias and variance decomposition for several learning models, which we discuss in later chapters. Bias-Variance Decomposition is for sum of squared laws and is for regression. Such a nice additive splitting of error into bias, variance, and noise is not possible for 0-1 loss because in classification, there is error only if we accidentally move to the other side of the boundary. For a two-class problem, if the correct posterior is 0.7 and if our estimate is 0.8, there is no error. We have error only if our estimate is less than 0.5. Various researchers proposed the different definitions of bias and variance for classification. So we see Friedman 1997 for a review.